Usually when we talk about human states of consciousness, there is this expectation of well, a very clear, reliable binary, like a light switch in your house.
Right. Yeah.
You're either awake and the light is blazing, or you're asleep and the light is completely off.
It is a very comforting way to look at our biology, honestly. We really crave those clear categories, activity versus rest, high metabolic demand versus low metabolic demand, conscious versus unconscious.
Exactly. But step into the world of deep meditation, and that light switch just completely shatters.
Oh, absolutely.
We are looking at a biological landscape that completely defies those neat little categories. So today, we are exploring this mind-bending biological shortcut. We are pulling from an excerpt of a book that explores the very bleeding edge where biology meets mindfulness.
And it's a fascinating text.
It really is. The chapter is literally titled Human Hibernation. And our mission for this deep dive is to explore the hypothesis that meditation is not just, a psychological tool for stress relief,
Yeah.
but a physical backdoor into ancient, dormant survival mechanics hiding in our DNA.
Yeah. And we so often think of meditation purely as a spiritual practice, but today we're stripping all of that away. We are looking at this strictly through the lens of evolutionary biology and raw survival mechanics.
Right.
Because the core premise here is that meditation is essentially a wake sleep. It's a state where the mind retains full conscious awareness while the physical body powers down into a state far deeper than typical rest.
Let's unpack the baseline biology of that for a second, because if you look at someone in heavy REM sleep, their body is resting, sure, but the engine is still idling.
Right, the basic functions are still running.
Exactly. The heart is pumping at a steady rhythm to maintain blood pressure. The lungs are actively drawing in oxygen, and, the digestive system is still processing. There is a baseline level of metabolic activity required just to keep the organism alive.
Yes, a constant burn of energy.
But the data on advanced meditators shows those numbers plummeting way, way below that baseline.
And that discrepancy is what forced scientists to look closer. I mean, there are well-documented accounts of Buddhist monks reaching levels of meditation so deep that their heartbeats and breathing become almost imperceptible to standard medical equipment.
Wow.
Yeah. For a long time, Western science didn't quite know what to do with those accounts, often just dismissing them as measurement errors or, pure myth.
Wait, I need to stop you there,
Okay.
because this is where the math doesn't add up for me at all.
Okay, what do you mean?
Well, if a human's heart rate drops to near zero, their brain is being starved of oxygen.
Right.
A normal person would suffer severe brain damage or die within minutes. How does deep meditation not just immediately trigger a massive stroke or a heart attack?
That is the perfect question. And it targets the exact flaw in how we usually think about human biology. See, you are assuming the brain's demand for oxygen remains constant.
Well, yeah, it usually does.
Right. If your heart stops right now, you die because your brain cells are still firing at full speed, demanding oxygen that is no longer arriving. But what if you could turn down the demand?
Oh, I see.
Yeah, if the metabolic demand for oxygen drops simultaneously with the supply, the cells don't starve, they just go dormant. And to understand how a mammal survives that state, we can't look at human sleep. We have to look at biology that evolved to withstand that exact near-death physiological profile.
Animal hibernation.
Exactly, animal hibernation.
Which is completely different from just, a really long winter nap.
Utterly different. Hibernation is a profound, systemic minimization of life activities. The whole goal is to reduce energy consumption to the absolute bare minimum required to keep the organism alive during incredibly harsh, resource-scarce environmental conditions.
Just barely clinging to life.
Exactly. When an animal hibernates, its metabolic rate slows down so drastically that it practically rides the razor's edge of clinical death.
And for you listening, this is where the biology starts to sound like science fiction. Let's look at the sheer extremes of how far hibernation pushes the boundaries of life. You have hedgehogs, for instance.
Oh, hedgehogs are wild.
Yeah, they drop into a state so deep you can literally pick them up and handle them, and they remain completely unresponsive, appearing totally lifeless.
Then you have bears, which provide a really fascinating contrast because they're the only carnivorous animals that hibernate.
Right.
Their version is considered a light hibernation. They only experience a slight drop in body temperature, and they can actually wake up if threatened. But physiologically, it is still astonishing.
Because of the heart rate, right?
Yes. A black bear's normal heart rate is about 40 to 50 beats per minute. During hibernation, it plummets to just 8 beats per minute. That massive reduction in metabolic burn is what allows them to survive for over 100 days without eating a single bite of food, drinking a drop of water, or even passing waste.
8 beats a minute is wild. But the bears have absolutely nothing on the North American box turtle.
True.
During hibernation, this turtle's heart beats only once every 5 to 10 minutes. 1 beat every 10 minutes.
It's hard to even comprehend.
And they effectively stop breathing through their lungs entirely, absorbing the microscopic amount of oxygen they need directly through their skin.
Yeah.
But the real hook here isn't just about surviving the winter. It's about a shocking side effect of this metabolic shutdown, which is massive lifespan extension.
The correlation between hibernation and lifespan is one of the most intensely researched topics in biogerontology right now. And to understand why, you really have to understand how aging actually works at the cellular level.
Right.
Every time a cell burns energy, every time mitochondria produce ATP, it creates metabolic byproducts, free radicals, oxidative stress.
Exhaust from an engine.
Precisely. Over time, this damages the cell's DNA and machinery. It is like driving a car. The faster and longer you run the engine, the more wear and tear you put on the parts.
So if you park the car in the garage and literally turn the engine off for half the year, the parts last twice as long.
That is exactly what happens. Generally speaking, in mammals, lifespan is dictated by metabolic rate, which usually correlates with body size.
Okay, so bigger animals live longer.
Right. A massive animal like an elephant has a very slow metabolism and can live up to 80 years. A tiny animal like a mouse has a heart that beats hundreds of times a minute. It burns through its cellular lifespan incredibly fast and is lucky to reach 3 or 4 years.
But the data completely falls apart when you look at hibernating bats, doesn't it?
It shatters the whole paradigm. If you take a hibernating horseshoe bat and compare it to a non-hibernating mouse of the exact same body size, the difference is staggering.
Because they're basically the same size.
Exactly. The mouse lives its fast-paced 3 years and dies. The hibernating bat, purely by virtue of hitting the pause button on its cellular metabolism for months at a time, can live for over 30 years.
Wow.
It's a tenfold increase in lifespan.
And we see this within the same species too, right?
Oh, absolutely. Individuals living in colder regions that are forced into long hibernation periods end up living significantly longer than their non-hibernating counterparts in warmer climates. By drastically reducing oxidative stress and cellular division during hibernation, they are literally delaying the biological clock.
Now, if you're listening to this, you're probably making the obvious leap right about now. Okay, sure, bats and turtles live longer, but they're genetically distant from me. I am a human.
Right, the human connection.
Exactly. And that is what makes the 2004 discovery of the fat-tailed dwarf lemur in Madagascar such a massive biological bombshell.
Oh, the dwarf lemur changes the entire evolutionary narrative. So from June to January during the dry season, this animal hibernates in tree holes for up to 7 months.
7 months.
Yes. It survives by slowly metabolizing the fat stored in its tail, often losing half its body weight. But the reason biologists care so much is that lemurs are primates.
They're on our branch of the evolutionary tree.
Exactly. Before this discovery, hibernation was mostly seen in lower mammals, rodents, and bats. Finding it in a primate proves that the genetic switch for hibernation didn't just die out millions of years ago. It successfully made the evolutionary jump into the primate lineage.
Which is huge.
It really is. It implies that this complex genetic hardware, the ability to safely plummet your heart rate, lower your temperature, and pause cellular aging, is likely still sitting dormant in human DNA right now.
So that brings up the million-dollar question. If we have that dormant primate hardware, are there real-world examples of humans accidentally turning this hibernation mode on?
The evidence says yes.
And it usually happens in the most terrifying circumstances.
Yeah. The most famous medical case occurred in 1999. A 29-year-old skier named Anna Bogenholm fell headfirst through the ice of a frozen stream in Norway.
Oh, wow.
She was trapped completely underwater for over an hour. When rescue teams finally pulled her out, she was clinically dead. No heartbeat, no breathing.
And her body temperature.
Her core body temperature had dropped to a staggering 14 degrees Celsius, which is about 57 degrees Fahrenheit.
Okay, again, going back to that oxygen demand problem we talked about earlier. If you drown in a warm swimming pool, your brain dies in minutes. How did she survive an hour underwater without severe brain damage?
It completely comes down to the precise sequence of events. Because the icy water cooled her brain down before the oxygen deprivation fully set in, her cellular metabolic rate plummeted.
So the demand dropped before the supply ran out.
Precisely. The cold essentially forced her brain cells into a state of suspended animation. The cells stopped demanding oxygen, and because they weren't demanding it, they didn't starve when the supply was cut off. It took a medical team hours to slowly warm her blood and restart her heart, but she woke up.
And it's not just freezing water either. There is the 2006 case of Mitsutaka Uchikoshi, a 35-year-old Japanese man who fractured his pelvis on a mountain and fell into a coma on the freezing ground for 24 days.
Yeah, that case is unbelievable.
24 days. His core temperature dropped to 22 degrees Celsius. He had no detectable pulse. Yet after being discovered and slowly rewarmed, he regained full consciousness with absolutely zero brain damage.
Now, these survival stories don't prove that humans can just, snap their fingers and hibernate, but they strongly suggest the biological capability is there.
The machinery works.
Exactly. If we trace our evolutionary history back far enough, mammals evolved from ancient reptilian ancestors. The vast majority of reptiles are cold-blooded and absolutely must hibernate to survive environmental extremes. The working hypothesis in the field right now is that we still possess these ancient survival genes. We have simply forgotten how to naturally trigger them because we evolved in warmer, more stable environments and, well, eventually invented clothes, fire, and shelter.
We didn't need it anymore. Which brings us to the modern scientific ambition. We know the hardware is there. We know it extends lifespan in animals. We know it can accidentally save a human life in freezing temperatures. So how do we harness it on purpose?
Well, we are already using crude versions of this in trauma centers today. It is known as therapeutic hypothermia or targeted temperature management.
Right.
Yeah, if a patient suffers cardiac arrest or a severe traumatic brain injury, doctors will intentionally pump ice-cold fluids into the body to artificially induce a hibernation-like state.
To slow down the damage.
Exactly. By slowing down the metabolic rate, they aggressively halt the cascade of cellular injury and tissue death. It buys surgeons precious time to fix the physical trauma. It's actually the exact protocol that saved Formula One driver Michael Schumacher after his catastrophic skiing accident back in 2013.
But the true end game for this research isn't just the emergency room, is it? It's the stars. NASA and the European Space Agency are pouring resources into artificial human hibernation for interstellar space travel.
Oh, the space applications are massive.
Think about a mission to Mars. If the crew is awake for the 8-month journey, they need tons of food, water, oxygen, and psychological stimulation. If you put them in hibernation, the spacecraft's resource load drops by a massive percentage.
The engineering logic is incredibly sound, but the biological execution is incredibly dangerous. Inducing human hibernation via severe temperature drops or chemical induction is highly experimental, and it brings us to the massive, often ignored roadblocks with cryonics.
Right.
The practice of chemically freezing a human body with the hope of reviving it decades or centuries later.
Right, because cryonics isn't hibernation. It's essentially freezing meat. To prevent the water in your cells from turning into jagged ice crystals that literally shred your cell membranes, cryonics companies replace your blood with cryoprotectants, basically medical-grade antifreeze.
And those cryoprotectants are highly toxic to biological tissue at room temperature. The physics and chemistry essentially contradict the biology.
It's like trying to freeze your smartphone in a block of ice so the battery never dies.
That is a great way to look at it.
Yeah, sure, the physical battery is perfectly preserved, but the toxic antifreeze chemicals you pumped into the casing just melted the delicate motherboard. And even if you somehow thawed out centuries later and, I don't know, invent nanobots to repair the melted hardware cell by cell, we have absolutely no idea if your photos, your contacts, or your operating system will actually boot up.
That is the ultimate critique of cryonics right there. It is a brute force physical preservation technique that completely ignores the continuity of consciousness. Even if theoretical nanomedicine could repair the toxic cellular damage, the information theory of the brain suggests that memory and consciousness might not survive the complete cessation of quantum electrical activity.
So you fix the body, but the person is gone.
Exactly. Cryonics preserves the hardware, but it might permanently delete the software.
Which brings us to the pivotal realization of this entire deep dive. If artificial freezing shreds our cells and toxic chemicals melt our biology, how do we safely tap into those ancient life-extending reptilian genes? How do we flip the switch without the ice? And the answer the research points to is astounding. Meditation is the ultimate natural trigger.
And the biological mechanism for how meditation achieves this is incredibly elegant. It relies on hacking your body's own sensory feedback loops.
How does that work?
Well, when you sit in deep advanced meditation, the absolute primary goal is unwavering physical stillness. Your body is covered in proprioceptors. These are built-in sensors that constantly relay movement and spatial data up the spinal cord to the brain.
So by remaining perfectly still for an extended period, you are starving those sensors of any input. It's like a motion sensor light in an office building.
Okay, yeah.
If you sit perfectly still at your desk for long enough, the room's sensors assume everyone has gone home and it shuts the power off. By staying absolutely motionless in meditation, you're depriving your brain's motion sensors of data until it assumes the body is powered down.
That is a brilliant analogy. I love that. When the reticular activating system in your brainstem stops receiving movement signals, it logically assumes you must have fallen asleep. In response, it actively shifts your autonomic nervous system.
It changes gears.
Yes, it inhibits your sympathetic nervous system, the network responsible for adrenaline and the fight or flight response, and it heavily stimulates your vagus nerve and the parasympathetic nervous system, which controls rest, digestion, and slowing the heart rate.
But here's the critical difference. You are not asleep. Your mind is brilliantly, consciously awake. And if you maintain that absolute physical stillness past the point where the body expects to enter a normal sleep cycle, the unconscious brain gets confused.
It faces a biological paradox. The body is completely inactive, breathing is shallow, but the typical neurological markers of REM or deep sleep aren't resolving.
Yeah.
So the brain's ultimate survival architecture just takes over. It assumes the organism is in an extreme dormant state, likely due to an environmental crisis. And that is the exact moment it signals the activation of those ancient hibernation genes that have been sitting dormant in your DNA for millions of years.
It literally flips the biological breaker.
Yes. The activation of those specific genes is what safely drives the vital signs, respiration, body temperature, heart rate, down to those near shock levels we see in advanced monks. Because it is an internally regulated genetic process governed by your own DNA rather than an external shock like freezing water, the body manages the physiological descent perfectly.
So no ice crystals.
No ice crystals, no toxic antifreeze, just pure evolutionary biology doing what it was built to do.
This completely reframes historical events that we usually just write off as myth. Think about the ancient legend of the Buddha meditating under the Bodhi tree for 7 days and 7 nights without moving, eating, or drinking. When you look at it through the lens of genetic hibernation and dropped metabolic demand, it stops sounding like a mystical fairy tale and becomes a very real, very extreme biological achievement.
It really does. And it also perfectly explains modern survival anomalies. Take the 2018 Thai youth soccer team that was trapped in the flooded Tham Luang cave system.
Oh, that's a perfect example.
12 boys and their coach were stranded in the dark for over 2 weeks in dire conditions, with practically no food and dwindling oxygen. Their coach, who had actually spent years as a Buddhist monk, instructed the boys to sit still and meditate.
They weren't just calming their panic, they were actively lowering their metabolic rate.
Precisely. By entering deep meditative states, they triggered that parasympathetic cascade. They drastically reduced their body's demand for calories and oxygen. In a zero-food environment, slowing your metabolic burn rate is the difference between starving in a week and surviving for over 2 weeks until rescue divers can finally find you.
I just love the profound implications of this for all of us listening. You know, meditation isn't just a mindfulness app you use to de-stress before your next corporate Zoom meeting. It is literally a backdoor into your own DNA. It is a way to hack your evolutionary biology. If NASA really wants to send astronauts on multi-year interstellar missions, they might not need billions of dollars in toxic cryogenics. They might just need to recruit expert meditators.
It really forces a complete redefinition of meditation as a whole. It is not an escape from physical reality. It is a highly specific biological mechanism designed to keep the mind brilliantly awake while allowing the physical body to safely descend into a profound hibernation-like state. It is the ultimate bridge between human consciousness and the most primal, ancient survival mechanics of the mammalian body.
It is absolutely incredible. Well, we want to thank you so much for joining us on this deep dive into these sources. We went from the cellular biology of aging in bats to humans surviving frozen lakes, all the way to hacking our metabolic rates through tear stillness.
It's been quite a journey.
It really has. But we want to leave you with a final thought to mull over as you go about your day. We've established that the genetic switch for hibernation didn't disappear, right? It just went dormant, waiting for the right signal, perfect stillness to wake up. So if our unconscious brain can be tricked into unlocking millions of years old survival genes just by us sitting perfectly still, what other ancient evolutionary superpowers are hiding away in our DNA, just waiting for us to find the right switch?
That is a great question.
Think about that light switch from the very beginning of our conversation. We are so used to thinking of ourselves as either just awake or just asleep. But the truth is, your biology is a massive, complex control panel of evolutionary dimmers and switches that we haven't even begun to fully explore.
It is a profound realization. The hardware is all there. Keep questioning those basic assumptions about what your own body is capable of, because there is always a deeper layer of biology waiting to be understood.
Until next time, keep digging into the fascinating sources around you. Take care.